Namaste dosto. Imagine you and your friends each have different heights. Even if the average height is the same, some groups might have friends who are almost the same height, while others have one very tall and one very short friend. This difference in how spread out the heights are, that's what we call dispersion in statistics. So, what exactly is dispersion? Well, it measures how much the data points, like those heights, deviate or differ from a central value, for example the mean, median, or mode. It helps us understand whether the data is tightly packed or spread out. When dispersion is low, values cluster closely around the center. For example, if all your friends' heights are very similar, there's low dispersion. But if the heights vary widely, we say there is high dispersion. Now, why is this important? Because sometimes two data sets may have the same mean, median, or mode, but their spread could be very different. To compare these spreads numerically, we use measures of dispersion. Some common dispersion metrics you will frequently see are the range, quartile deviation, mean deviation, and standard deviation. These help us capture and compare how spread out or variable data sets are. Picture this. Imagine a line plot with two data sets. Both have the same mean but very different spreads. One is tightly packed, the other more scattered. That visual difference is the essence of dispersion. Are you ready to explore these measures in detail? Let's dive deeper together. Welcome back. To begin exploring measures of dispersion, let's start with the simplest one, the range. Think of range like measuring the span of a cricket pitch. It's just how far apart the largest and smallest observations in a data set are. In short, the range is calculated as the difference between the largest value, which we'll call L, and the smallest value, S. So, range equals L minus S. Let me say that again slowly. Range equals capital L minus capital S. To make things even more precise, we have something called the coefficient of range, which is calculated as the difference between L and S divided by their sum. So, coefficient of range equals open bracket L minus S close bracket divided by open bracket L plus S close bracket. But here's a caveat. Range is highly affected by extreme values or outliers. For example, if there's just one very large or very small number in your data, the range might be misleading. So for data sets that are large or skewed, range might not be the best measure. However, range is quite useful for quick comparisons when outliers are minimal and the data distribution is almost uniform. To imagine this better, think of a number line comparing two datasets, A and B, both having the same median, but dataset A has a wider spread because its maximum and minimum values are further apart. That's a direct illustration of how range shows dispersion. Shabash, keep this simple but powerful idea in your mind. Now let's move to a measure that's smarter than range, especially when dealing with skewed data, quartile deviation. Picture this as focusing on the middle 50% of your data, ignoring the extreme outliers that might skew your view. Quartile deviation, or QD, is half the difference between the third quartile, Q3, and the first quartile, Q1. Simply put, QD equals open bracket Q3 minus Q1 close bracket divided by 2. I'll say that again. Quartile deviation equals the difference between the third quartile and first quartile divided by 2. There's also a coefficient for quartile deviation, calculated as the difference between Q3 and Q1 divided by their sum. Coefficient equals open bracket Q3 minus Q1 close bracket divided by open bracket Q3 plus Q1 close bracket. Because it focuses on the central 50% of data, quartile deviation is less influenced by extreme values. So, it's very useful in skewed data sets, such as income distribution or test scores, where you care more about the core spread than the outliers. Imagine a box plot showing the minimum, first quartile, median, third quartile, and maximum values. This visual makes clear where the central 50% lies, highlighting the quartile deviation. Excellent so far. Next up is the mean deviation about mean. Think of it as the average distance of all data points from the mean without caring whether they are above or below it. This measure captures the typical amount by which values deviate or differ from the average. Formally, mean deviation is the arithmetic mean of the absolute deviations from the mean. For group data, it's calculated as the sum of frequency times the absolute value of class mark minus mean divided by total frequency. Said slowly, mean deviation equals sum of f sub I times the absolute difference between x sub I and x bar, all divided by sum of f sub I. Here, the absolute values are crucial because otherwise positive and negative deviations could cancel each other out, giving a false sense of low scatter. Mean deviation considers all data points, unlike the range, which only looks at two extremes, making it more reliable for typical spread. However, despite this advantage, mean deviation is less popular than standard deviation in statistics. Imagine a histogram where the mean is marked, and vertical lines show each data point's deviation from that mean. The average length of these lines is the mean deviation. Keep that image in your mind for better understanding. Now, things are getting interesting. The most reliable and widely used measure of dispersion is the standard deviation. Think of standard deviation as the root mean square deviation. It weighs larger deviations more heavily than smaller ones. For ungrouped data, the formula is sigma equals the square root of sum of open bracket x sub I minus x bar close bracket squared divided by n. Let me repeat that clearly. Sigma equals square root of the sum of the squares of the differences between each data point x sub I and the mean x bar, all divided by n. For group data, it's very similar. Sigma equals square root of sum of frequency f sub I times open bracket x sub I minus x bar close bracket squared divided by sum of f sub I. Repeat once more. Standard deviation equals square root of sum over all classes of frequency times square of difference between class mark x sub I and mean x bar divided by total frequency. A low standard deviation tells us that the data points lie close to the mean, meaning less variability. Conversely, a high standard deviation indicates values are more widely spread around the mean. Keep in mind, standard deviation is sensitive to extreme values but is always non-negative. It forms the foundation of advanced statistical methods like hypothesis testing and regression. Imagine a classic bell curve showing the mean at the center and shading areas one standard deviation above and below it. This image helps visualize where most data points lie. Arey wah, understanding this opens doors to powerful data analysis. Let's build on standard deviation and introduce the coefficient of variation, or CV, which tells us how big the standard deviation is relative to the mean itself. This is very useful when comparing variability across datasets on completely different scales. The formula is coefficient of variation equals standard deviation divided by mean times 100%. So, CV equals sigma divided by x bar times 100%. A lower CV means the data is more consistent relative to its mean, while a higher CV indicates more variability. Think about comparing returns onto different investments. One gives small gains but very steady, the other gives big gains but with wild swings. CV helps decide which one is relatively more stable. This makes the coefficient of variation perfect for comparing datasets like investment returns, test scores, or productivity metrics from different units. Picture a bar chart comparing CV values of multiple datasets side by side. That's how analysts quickly see which data is more variable in relative terms. Excellent job following along. Time to see these concepts in action. Suppose you have grouped frequency data with class marks and their corresponding frequencies, and you need to find the standard deviation. Recall the formula for grouped data. Sigma is the square root of the sum of frequency times the square of difference between class mark x sub I and mean x bar divided by total frequency. Step 1. Calculate the class marks x sub I, usually the midpoints of class intervals. Then multiply each x sub I by its frequency f sub I, sum these products, and divide by total frequency to get the mean x bar. Step 2. For each class, calculate the square of the difference between the class mark and the mean, multiply by the frequency, and sum all these values. Finally, take the square root of this sum divided by total frequency to get the standard deviation. With your working column-wise table neatly arranged, you verify the calculations and ensure units stay consistent. Interpreting the final sigma value tells you how spread out your group data is. Shabash! Practice this to build confidence. Let's quickly recap what we learned about measures of dispersion. First, range equals largest value minus smallest value, and its coefficient equals open bracket largest minus smallest close bracket divided by open bracket largest plus smallest close bracket. Next, quartile deviation equals 1/2 of the difference between third quartile and first quartile, with coefficient equal to their difference over their sum. Then, standard deviation sigma equals square root of sum of squared deviations divided by total number, and coefficient of variation equals sigma divided by mean times 100%. Remember, dispersion measures tell us how data varies. Standard deviation is the most reliable measure. Coefficient of variation lets us compare datasets on different scales, and quartile deviation is robust against outliers. So, the next time you see a set of numbers, you'll know not just the average, but also how spread out or consistent those numbers really are. Keep practicing. And here's a quick question for you. If two datasets have the same mean but one has a much higher standard deviation, which dataset is more consistent? Think about it. Pause. Exactly. The one with the lower standard deviation is more consistent. Well done, Beta. Stay curious and keep exploring the fascinating world of statistics. Until next time.